Okay, so let me tell the following thing, which is a little bit disconnected from the other course, but it is still nice to learn. Uh, so it's about wave equation in the arbitrary metric. So 1 plus 1 wave equation. So what I mean is the following equation. It is sum from I j equals 1 to 2 d dxi or maybe di. d, let me write it this way. d dxi some aij that depends on x1 and x2. du in dxj equals to 0. So in this way, in a sense, this derivative acts on this product. And determinant of this matrix is negative. So I will say a few words about the origin of this AIJ. So all this starts from a metric on pseudo-Riemannian manifold. In a sense, there is a 2x2 matrix that depends on coordinates, and it defines the following tensor. Gij of sum over ij, gij of x1, x2, dx1, tensor dx, sorry, dxi, dxj. So this lives in cotangent in cotangent bundle. In a sense, we take tangent bundle, we take dual vector space, so dual bundle to it, and then we take its second power. So this tangent vectors dxi and dxj are dual to d in dxi, d in dxj. In a sense, dx I of d over dxj equals to delta ij. So it's a dual basis. So there is this object, and there is another object with the inverse matrix. So there is sum over ij g ij d dxi tensor d in dx j with jij equals to g to gij inverse. Maybe better to write like g inverse ij. So this object defines a quadratic form on cotangent space, and this on tangent space, and this defines a quadratic form on cotangent space. And this object can also measure a distance on a manifold. In a sense, if you substitute an infinitesimal shift into this metric. If you imagine that dx are some small variation of dx, then this will be a square of distance between 2 points. And this other object which defines a scalar product on tangent bundle looks similar to a differential operator, but it's not a differential operator. If you want to write a differential operator, namely the Laplace operator, we need to construct the following object. So Laplace operator in this curved metric is the following object. So Laplacian of u is 1 over square root of determinant of this metric, sum over ij dn dx dxi square root of the determinant gij du in dxj. So it can be derived in some way, but the main point is that this differential operator transforms nicely when we perform all possible changes of coordinates. In a sense, we have some transformation of this metric gij, and this is precisely what happens with differential operator and the change of coordinates. So it's in a sense, yes, this operator is independent of the choice of coordinates. It depends on metric, but not on the choice of coordinates. So I should write here that this notation means determinant of gij. So if you consider this operator, we are sure that if you consider operators of this form, we can be sure that their transformations are governed by differential geometry. And now, are there any questions about this? So, it's actually. Yeah. Which? This? Oh.
Yeah, the first one and the one with where the indexes are on top. G, apex,
so there are simply different. So there are two inverse tensors. This tensor is is a section of square of a tangent bundle. It is this lives in the square of a tangent bundle. and you can multiply them and get an identity operator, because the fact that it lives in the tensor square means that it acts from a tangent bundle to a tangent bundle, and this one acts in different direction, so they can be multiplied, and you will get a identity operator. So this and by multiplication, I mean that we should we should pair these vectors of tangent space with these vectors of tangent space. So the result of this multiplication will be sum over I, dxi, a tensor d in dxi, which is the identity operator that acts from so this identity acts from tm to tm. Yeah, to star. It doesn't matter. We can, of course, put them from the very beginning, because otherwise we would need to change them. So this follows simply from the fact that these two matrices are inverse to each other. So, our statement this yeah. So are there any other questions? So, the statement that this Laplace operator is invariant is non-trivial. It should be derived somehow, but let us take it for granted. Mm, so. Mm, So we have some we have a relation that this matrix A is square root of a matrix times so Aij Gij. We can notice that there is such a relation. Mm. So our strategy to bring this equation to a reasonable form is to bring a metric to the form mm, mm, mm. So actually everything is symmetric, so I will avoid, I will omit this tensor product here. So we want to bring it to the form some function that depends on everything, x1, x2, times dxi d eta. Maybe let us write here xi and eta. Oh, no. So if you succeed in doing this, then the matrix appearing in this equation will have the following form. So this metric has a form. Maybe let us put here 2. So this Jij has the form. So if this is done, then metric Gij has the form 0 f 0. So a determinant of this metric is, or square root of determinant of this metric is an absolute value of determinant of this metric is f. So an a that equals to square root times Gij. What does it equal to?
But it's minus f squared. You can't take the square root. For the determinant of g.
So it's square root of the absolute value.
Square root of absolute.
Yeah.
So it's just f g I j.
No, but Gij, so G, which was the initial.
Sorry.
Yes. Mm-hmm.
So then is that 2 to 1?
Yes. 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 So we see that this matrix defined in this operator becomes constant, and our equation becomes simply dxi d eta of u equal to 0. So dxi d eta of u equals to 0. And more generally, Laplace operator of u becomes 1 over f. So more generally, so but let us now think why this strategy works. So we have this expression d I j of dx times dxi dxj sum over j dxi dxj, and we want So if you compute this metric on some vector, we can substitute here some vector uh, v, where v is uh, sum of vi, d in dxi. And this will be a sum of, this is a tangent vector. This will be gi j vi vj. Ij. So we can look for vectors such that this equals to 0. Or we can write it in the condensed form that it is this metric that equals to 0. So what do you think? How many solutions does this equation have? So for example, it is something like v x squared minus vy squared equals to 0.
Has two solutions.
Well, 2 up to the overall factor. So this equation defines two two directions in one point. So tangent directions or tangent lines at each point. So so in this case, it is this cross, and it will be the same in all other cases. It looks locally the same. So, so physically, this directions can be called light geodesics, or light like. I don't remember precisely the term. So we have the following picture. Uh, Mm. We can also integrate the distributions of tangent lines. In sense, we can find a family of lines that are tangent to each of them. So we have a picture like this. There is our manifold, and there are two systems of lines such that our metric restricted on these lines is 0. So if we now choose two variables that parameterize these families of lines, families of geodesics as coordinates, then our metric will have precisely that form. Oh, in a sense, there are two functions that describe the geodesics. We have some psi of x1 and x2 equals to constant. So where in this constant we can switch between different lines. And the second family is described by some eta of x1 and x2, 1 and x2 equal to constant. So x and eta are our desired function, our desired coordinates. So and they are defined by this equation that sum of ij dx so dij dxi dxj equals to 0. So this is the equation defining these two families of lines. Of curves. And x and eta are initial conditions for these equations. So let us see how this works in some particular situation. And well, maybe I should ask, is the idea clear or not? Maybe it's better to write something like this, that there is some function uh, a of x1 and x2, which can be called xi, and this xi is constant. And this is some other function, b of x1 and x2. Parameter.
From the regular coordinates to the desired coordinates, what are becoming the geodesics on the manifold?
This light line, like geodesics, become either xi constant or eta constant. And if you ask about different geodesics, then they can be whatever, because Laplacian has this prefactor and metric has a prefactor. So it's only about light-like geodesics.
But you change the coordinates, and then the metric changes. But what else changes?
The metric and everything else, all the differential operators are expressed in terms of metric. So is it okay or not? So if you do something like this, then we are sure that changing a change in eta with a fixed xi describes a geodesic with so it describes a light like a geodesic. In a sense, vectors tangent to this curve have zero lengths. And the same is true for another coordinate. So if you have such a situation, that this is precisely what is described by this metric. If you substitute a vector that has only one non-zero component tangent to dxi or tangent to d eta, then its length is zero. So if you construct coordinates in this way, then so precisely in the case. So let us show how it works. Let this Gij be xy xy minus xy 1/2 squared minus y squared 1/2 squared minus y squared. So it's let's compute the determinant of this matrix. This metric. Well, this minus x squared y squared minus 1/4 squared minus y squared squared. So in total, it's combined into minus 1/4 x squared plus y squared squared. So, and the square of g times this matrix inverse is this square of determinant by the overall sign, because we need to divide by determinant and so probably here change sign. So yes, it seems that this works.
And we have to divide never mind. You put the factor I found.
So we divided by determinant and then multiplied by square root of its absolute value.
Okay.
So differential operator that is described by this metric is the following. So, or the equation described by this metric is the following. So it is dx, so d in dx minus xy d in dy and apply the same operator. Oh, sorry, d in dx apply the same operator on the same term with xy d in dy xy du in dy. And then this cross terms. Maybe, yes. So we have an equation of this kind. So if you try to write it as a differential, as an equation with differential operators acting on u, you also get some first derivatives, but we don't care about them.
What about the time derivatives? Because aren't we supposed to have one dimension of space?
But
one dimension of time?
oh, but the question is who is time? How to choose it in this in these coordinates. It depends on x and y. So we only know that this metric is of type 1, 1. It has it has negative determinant, which means that one eigenvalue is positive, another eigenvalue is negative.
Oh, okay. So this is the wave equation, and we're not missing time derivative.
Yes. So space and time are somehow related to this x and y. But it can be chosen in different ways. Yeah, so we have this equation, and what is the corresponding metric? Corresponding metric is this expression, dx squared minus dy squared over the diagonal elements, dy squared times xy plus dx dy times x squared minus y squared. And we want this to be equal to 0. So this can be written as a differential equation on x and y. So let us divide by dy. So dx by dy squared times xy. Maybe let us also divide by xy. Dx by dy squared minus 1 plus dx and dy x over y minus y over x. Maybe we could maybe we can solve this equation even let us solve it simply as a quadratic equation without inventing anything. So dx and dy is minus 1/2 x over y minus y over x plus minus square root of 1/4 x over y minus y over x plus 1. Squared, sorry. So this is minus 1/2 x over y minus y over x plus minus square root of x over y plus y over x squared. So dx and dy, I missed 1/4 here. So there are two options for dx and dy. One option is when we take plus sign here, and this will equal to y over x. Another option is dx and dy equals to, when we take the minus sign, it will equal to minus y over x, minus x over y. So there are two roots of this differential equation. And if you want to solve them, then we simply combine this x in dx, y in dy, and this equation becomes d of x squared over 2 equals to d of y squared over 2. And this equation becomes y dx plus x dy equals to 0. So this equation tells that d of x squared minus y squared equals to 0. This equation tells that d of xy equals to 0. So they both tell that some function should stay constant. And what I was saying here is that we should say that this constant, these two constants that parameterize these families of curves should be chosen as xi and eta. So x squared minus y squared is xi, xy equals to eta. So we have some picture of this form. There are some hyperbolas of this form that describe a fixed eta. This is x and this is y. And are the hyperbolas of this form. So there is a choke. Maybe that. So and this is xi constant, xi equal to constant. So and this was our original equation. So going back to this equation, how would you write its general solution in terms of x and y?
we specify boundary conditions when we look into the
uh,
variables?
No, the question about boundary conditions is tricky. Um, in a sense, we should choose some space-like or time-like directions and fix um, this function and its first derivative. I'm asking about parameterization of all possible solutions of this equation. So. mm, of what we call this equation star. So what do you think it is?
Or we should just change the variables and then it'll simplify, right?
Well, actually, there is nothing to simplify. In a sense, we know that this change of coordinates should bring our wave equation to the form some function times dxi deta of u equals to 0. So dxi deta of u equals to 0. So u is f psi plus g of eta. But it is, so if you write it in terms of original coordinates, then it will be f of x squared minus y squared plus g of xy. So that's it. And I can leave it as a homework to check that this is indeed a solution of this equation. So I was saying this to show that there are some exceptional cases, like in 1 plus 1, maybe 1 plus 0, a trivial case, in which this classification of all the second order differential equations can be extended beyond the case of equations with constant coefficients. So, namely, this this construction teaches us that any wave equation can be at least locally transformed to canonical form u xi eta equals to 0, even if the original equation had arbitrary coordinate dependency in all its coefficients. But it does not work in higher dimensions, and it does not work even in 1 plus 1 when we add the free term or some other derivative terms here, because this overall factor cannot be removed. So. By the way, this metric is called conformally flat. In a sense, it is a kind of a constant metric, but with the overall factor. And the main property of this Laplace operator in 1 plus 1 or 2 dimensions is that when we take our metric and multiply it by an arbitrary scalar factor, then this inverse metric is divided by that factor, and square root of determinant is multiplied by that factor, because the determinant, let me, you actually saw it here. that if you multiply original metric by an arbitrary function, then this function cancels from the Laplace operator. So. So plus operator is always will always be psi d eta. So reflects. So result we see is a combination of two facts. The first fact is that in that the equation in 1 plus 1 is invariant under scaling of the metric by an arbitrary function. And then the second fact is that any two-dimensional metric can be brought to this canonical form when it is constant canonical metric times some function. So it is true for 1 plus 1 and also for 2 dimensions. So are there any questions on this?
The general solution was from 2 lectures ago, right? End of the 2 lectures ago.
Something in the end of the second lecture and beginning of the third one. Yeah. But it's simply no calculus. We have a mixed derivative of function equal to 0. Then it tells us that d eta of u is a function of eta only, and then we integrate it again.
And
So
under the change of coordinates, this still has to have the same form of solution. So you just have to remember the canonical form, and then you can derive from that the form of the solution.
what do you mean? Oh, in a sense, solution transforms like a function. So it was f of psi plus d of eta, and we should simply know who psi and eta are. So. And by the way, this lines with psi and eta constants are also called characteristics. So as in the flat case, all this propagation, all these perturbations will propagate along characteristics. So if you create some initial condition at some point, for example, here, and run the evolution, then it will propagate along these two lines. And other parts of the plane will be unaffected.
There's some unlimited ambiguity on the direction of the characteristics, right?
No, in a sense, yes, and there is some singularity.
For each coordinate, there are two potential directions or some maximum to the propagate.
Let me think. So what can we say about 0? Actually, never thought what it happens at zero, but this zero is a really bad point because determinant of this metric is zero, so we can only ask what precisely happens when we approach that point. But I don't know if it is interesting or not. Yes. 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 So let me think. Yes, it is zero, not infinity. So, uh, are there any other questions? Yes. Shall we make a break or shall we continue? Yeah. So, how long? For 5 minutes or more? Yeah, let us go back to a topic from the previous, from the end of previous lecture. Maybe turn on it. So we were studying the following problem with initial and boundary conditions. So, so our equation was as before: ut minus uxx equals to 0, and one problem was this, that there is x and t plane, and we asked this u of 0x be u0 of x, ut of 0x be u1 of x. And here we could choose different boundary conditions. One option was to ask this to be 0. This is called Dirichlet. So, and the idea of solution was the following: that we can say that this solution can be completed by another half to a solution on the whole line. you so we can construct a solution that is antisymmetric with respect to 0.
How do we know that the boundary at x equals 0 won't affect our solution if we first solve it on the whole line?
But we know that this solution satisfies this boundary condition from the very beginning, because sorry, it is minus u of t minus x. So let us see how this works at the level of pictures. So it looks like this. We have some profile, like in this triangle. Let us place it somewhere far away from 0. We have a triangle, and we have its mirror image. So this point x equals to 0. So this is t, this is x. So this is u. How to draw it better? This is u, and this point works like a mirror. So there is a completed part of initial condition, and when we start evolution, then these two triangles split. So one moves in a negative direction, another moves in positive direction, and the same happens to these two triangles. So when they reach 0, then these two triangles start compensating each other. So they pass through each other, and a resulting picture when all this happens looks like this. So we have one triangle that was moving rightwards, and another triangle that came from the negative semi-axis, and it is reversed, and it's moving in the same direction. And we also have this mirror image of the same picture, which is not very important because we don't see it anymore. So,
you said this strategy with the boundary conditions is called, what was your name for it?
Mirror method.
Is it the same in like electrostatics books? They use method of images, so they.
Yes, of course. There are different kinds of images, because when people talk about prosthetics, they can also talk about mirrors in some spherical surfaces. There are some other trivial examples, but the basic idea is the same. That boundary conditions on some surface or on a line can be realized as a compensation of the original source or initial value and its mirror completion. So this is mirror. And so on, this process can be interpreted as a reflection from the mirror at zero. So when this reflection happens with the phase inversion. In a sense, the shape of a reflected wave is reversed respect to the phase of incoming wave. So are there any questions about this? Yeah, so let us consider another case, namely Neumann boundary conditions. Maybe I can erase this. So it's well the same picture, but but here ux of 0 and of t and 0 equals to 0. And here again, u equals to 0, ux equals to u1. So idea is very similar. We should simply take another completion of u, which in this case will be symmetric. So Tn x will be u of Tn minus x, kind of mirror completion. So when we take derivatives of this function, dx of u of Tn x will equal to u x of Tn x will equal to minus u x of Tn minus x. So if you put x equals to 0, then u x of t0 is minus u x of t0 is 0. So the picture that is analogous to that one is the following. This is the mirror image. And they again start moving. And we also see a picture with a reflected wave. But this time the reflected wave has the same phase. In a sense, it's not reversed. So Any other question? Yeah. Last time I told that there are these two types of boundary conditions, and there are also mixed boundary conditions which will not study. But actually, there is one more uh, interesting and useful case, which is actually the simplest one in some sense. Maybe it's mm, oh, no, not simpler than this boundary condition on half line, but mm, still nice. We can impose periodic boundary conditions or anti-periodic if you like. So yeah, it should work.
I have a question about the Dirichlet boundary condition. I thought when you define the boundary at t equals 0, I don't understand why we have another part of the solution below. Sorry, that's u at different time slices on the x-axis. Okay, never mind.
So it start. So this triangle splits into two.
Yeah, from last time.
Yes. Yes. So this might be hard to realize for the string because our intuition tells that a finite string should be fixed at 2 points. But if you think about systems like some elastic ring or some oh, it is either some elastic ring that can move either in this direction, or there might be also elasticity waves propagating longitudinally in this ring. Or we can also think about some limits of finite systems with some masses connected by springs. There are also waves propagating in this system. So they can move on the string. Yeah, so periodic boundary conditions mean that U of periodic or anti-periodic boundary conditions mean that U of t and x plus L, where L is a length, it can be chosen equal to 1. Maybe, well, doesn't matter. it's the same as well, plus minus u of t t and x. So at the level of these pictures, it looks like this. We have a real line on this is time direction. Have a real line with points 0 and L, and this this line should be identified with this one. So it is a cylinder. So x coordinate lives here, and t coordinate lives here. So let us actually focus on this plus case, because minus because antiperiodic solutions can be constructed from periodic by doubling the interval. Because if something is antiperiodic with the step L, then it means that it is periodic with step 2L. So the basic problem is a solution of this equation on a ring. And let us think if we are able to solve it. So we know that locally, again, this u of t and x can be written u of t and x is given by f of x plus t plus g of x minus t. And we also have some initial conditions for the interval from 0 to L. F of x plus g of x equals to 0 of x, and f prime of x minus g prime of x equal to u1 of x. So this is written for x from 0 to L. But we can easily extend this to the whole line. We can simply say that this u is extended as a periodic function. So So there might be some problem with integration of u1, because if we integrate u1, then it will not be periodic. It will receive some extra shift when we move by one period, but it can be easily removed by simply adding a constant times t to solution of the equation. So we can make average speed of points of this ring equal to 0, and then integral of u1 will also become periodic.
I missed that. Could you please explain again what we do to fix the periodicity after we integrate U1?
Okay, so we have this equation minus uxx equal to 0 with two initial conditions. U0 of x, we have u0 of x, have u1 of x. And but we can consider another solution of this equation, which is a solution. It's easy to check that u tilde of t and x will be defined as u of t and x plus constant times t. Then again, u tilde t minus u tilde xx equals to 0, and here, so what happens with this initial condition? What happens with the initial value? Yes, and with the next one. Yes. So the integral from x to x plus L of this u1 of x of u1 tilde from x to x plus L of u1 tilde of x dx will equal to integral from x plus to x plus L times u1 of x dx plus c times L. So we can adjust this c so that it equals to 0. Not
Why don't we extend U0 and U1 by calculating them? How do we get the problem of
the only question is, in a sense, the question is, do we have anything special at point 0, which is identified with point L? So, if we care about differentiability, we should impose this condition on the initial conditions. and some this u0 and u1 will be differentiable. But you might also notice that I do not really care about differentiability, because it is some outrageous thing which we need to discuss later. But actually, I was substituting some functions that have discontinuities even in the first derivative into this equation. So I simply obtained this formal solution, 50 plus x and plus f of x minus t, and substituted an arbitrary function. So this will be justified later, but the point is that it does not really matter. And if you substitute something that was differentiable from the beginning, it will stay differentiable. And so, for example, if this was the question, let me see. Let me think. No, probably the question was, should we say that the first derivative is also the same here and there?
Well, if u0 in 0 and L must be the same value, and if we should ask.
Yes, yes, it's true.
And also maybe if
Right.
u1 is 0 and u1 and L are different from 0, maybe we should first reflect and then translate.
Initial conditions should be consistent with boundary conditions. Otherwise, it doesn't make sense. We had this problem even here, because there is a point 0, 0, which is described at the same time by u of t0 at t equals to 0 and by u0 of x. So u0 of 0 should be 0. Otherwise, a boundary condition is consistent with initial condition. Yes, and thanks for asking this. So yes, we should also impose another condition for the first derivative. That otherwise this will not be. So let me think. No, probably it will not be a well-defined problem. Actually, didn't think about counterexamples, but probably it's easy to construct. So yeah, we can consider locally difference. So yes, it's easy to construct counterexample if you don't impose the second condition, because we can look at this problem locally. In a sense, we have some condition on u at we have some condition for u around 0 and around L, and we can consider sum and difference of this function around 0 and around L, and it turns out that one function has this condition that it should be 0, and another function isn't constrained if you don't impose a second condition. So yes, it should be imposed. Yeah, so Okay, and if we extend this initial conditions in this way, then we can simply take this formula and use it. So we will have the same pictures. Maybe I can erase this blackboard. So we will have pictures like this. There is this circle. There is some triangle, and this triangle splits, starts moving in opposite directions. Then they move through each other. Oh, you can draw it forever, since there are two triangles that move in opposite directions. And why is this on this case interesting? This is because it can be used to describe two boundary conditions. For example, imagine that we have imagine that we try to combine this condition with another condition, that this function should be anti-symmetric with respect to 0. So with respect to 0 and with respect to some other point. So there's not that much time since it's almost over, and I will simply draw a picture. So and then write a formula. So imagine that we have the following circle of length L, and we put two mirrors here and at the point L over 2. And this mirror flips the value of a function. So if we have some triangle here, then its mirror image should be reversed. So we have two boundary / periodicity conditions. Tn x equals u of Tn x plus L, and second that u of t minus x equals to minus u of Tn x. And as a corollary, it's also anti-symmetric with respect to this point. So these boundary conditions are equivalent to Dirichlet boundary conditions on the interval from 0 to L over 2. So it looks like this. This is t, this is x. We have some initial condition here, and we have two boundaries with Dirichlet boundary conditions. Assume that u is 0 here and there, which corresponds to a string fixed at 2 points. Like this. And we already know how to solve this problem. So we can think about this picture as about a sequence of infinite mirror reflections. So we have a mirror at point L2, it adds a mirror image of this interval, then another mirror reflects everything, and we have this whole interval drawn again and again and again. So this allows us to write a general solution of the wave equation on the interval. And you see that it's slightly more complicated than on a line, because any perturbation will stay there forever. It will reflect from both boundaries, but and this should be taken into account. So if you try to write the analytic formula for a solution of this equation, it will involve an infinite sum, because so of course you can write you can formally write a function u0 of x plus t, but you should remember that this function. So we're finishing. So we have a function that is actually an infinite sum of its copies shifted by L. Yeah, and so this was the good news about the wave equation 1 plus 1. And the bad news is that all the things exist only in 2 and 1 plus 1 dimension for Laplace and for the wave equation. If you go to higher dimensions, or if you add a term to this equation, then all this breaks down, and we will have more complicated formulas. So, yeah, are there any questions? Okay, then thanks for your attention, and see you in 1 week.